Hello everyone, my name is Jeremy Wallace. I'm a Specialist Solutions Architect here at Amazon Web Services. I'm excited to dive deep today into AWS RoboMaker simulation and discuss some common use case patterns for using cloud computing in robotics development. Today, we'll start with a quick history and introduction into the benefits of using simulation in robotics. Then, we'll deep dive into running simulations in the cloud with a couple demos on how to use AWS RoboMaker. Finally, I'll walk you through two use cases for running simulations in AWS with RoboMaker: automated regression testing in CI/CD workflows and fleet simulation with multiple robots. Just a quick note, throughout today's presentation, I've included a few AWS Primer slides to introduce services that are important to know when talking about robotics architectures in the cloud. These solutions leverage the Robot Operating System, ROS. For those new to ROS, it is a flexible framework for building robot applications that was designed to encourage collaborative robot application development. We won't discuss the fundamentals of ROS in this presentation, but if you're interested, please check out ros.org to learn more. Okay, so let's start out with the benefits of using simulation in robotics. While simulation in robotics is relatively new, the concept of using simulation dates back to early civilizations. Roman armies trained their soldiers by recreating battle scenarios using wooden swords. One of the key reasons why the Roman army was so successful was their training. Practicing with wooden swords reduced the chance of injury. Later on in the Renaissance era, Leonardo da Vinci was known to build scale models of his inventions. He did this to test different configurations and quickly iterate, optimizing the design before building time-intensive and costly full-size prototypes. Today, simulation is used across almost every industry. In healthcare, surgical students learn new techniques and practice on everything from simple sutures to advanced robotic surgery before performing these operations on humans. In agriculture, farmers use simulation to determine land management strategies and adapt for the impacts of climate change. By running the initial crash tests in simulation, car manufacturers can reduce the number of destructive tests they need to do with actual cars. Finally, simulation in aviation dates back to the 1920s. Today, flight simulators are a mandatory part of pilot training and used across the industry, from commercial airlines to space travel. A common result of all these examples, from combat training in ancient Rome to NASA's rover pilots, is simulation enables faster iterations and lowers the cost of mistakes. This leads to accelerated learning cycles and an increased pace of innovation. Simulation benefits are particularly valuable in robotics development and prototyping. First, robots can be costly and access to a robot might be scarce. By using simulation, every developer can easily access a virtual robot, and when unexpected behaviors inevitably happen, there's no risk to expensive hardware. Secondly, developers may want to specifically test for conditions that may be unsafe or risky. In simulation, you can speed up the clock to faster than real time, enabling developers to run tests that would likely be very time-consuming or maybe not even practical on actual robots. Next, you can expand the coverage of your tests in simulation with parameters that cover all of the conditions your robot will encounter. For example, you could run a set of tests in 100 different room layouts. This would be very difficult with physical robots. When using simulation, you can easily repeat scenarios with specific conditions that led to unexpected behaviors in the past. And by running regression tests in simulation, you can ensure your robots meet well-earned customer expectations. Finally, teams can use simulation to decouple development workflows, enabling various teams from front-end UI/UX application developers, robot software application developers, and engineering teams working on the physical robots to work independently and in parallel. When robotics companies use simulation early in their development cycle, they typically have a faster time to market, an increased feature release velocity, and introduce less software defects during code iterations and in production. Today we'll talk about how AWS RoboMaker can make it easy for your company to get started with simulations. 3D simulators are popular tools for robot application developers. Here are some of the key components. First are the 3D models, or mathematical representations, of an object's physical body in three-dimensional space. Next, 3D simulators commonly include a physics engine, which simulates realistic movements by calculating physical systems, like rigid body dynamics for collisions. 3D rendering engines are used to build and render graphics in the environments. And finally, 3D simulators for robotics support a variety of middleware software that can be used to accelerate the development of robot applications. There are many 3D simulators available to robotics developers. However, today we'll discuss Gazebo, a commonly used simulator supported by Open Source Robotics Foundation, OSRF. Gazebo supports multiple 3D model types and physics engines, a 3D rendering engine called Ogre, and interfaces with a few different middleware software, including the robot operating system, which I'll reference throughout this presentation. AWS RoboMaker supports Gazebo 7 and Gazebo 9 today, the Open Dynamics Physics Engine, Ogre, and ROS applications. All right, so at this point, we've determined that using simulation in your development workflow can provide multiple benefits, from increased feature release velocity to a faster pace of innovation. However, there are some key challenges and blockers developers face when getting started. First, creating 3D model assets to build a virtual representation of your robot, along with any objects in 3D worlds, is difficult. Infrastructure required to run simulations is hard to configure and standardize across the team. Then scale when you need to run compute-intensive simulations or run many simulations concurrently. This is particularly challenging when your simulations must communicate with external applications and control systems, or if you have complex networking configurations. Finally, it's hard to get consistency across developers' local simulation environments and create an easy way to automate your simulation workflows. AWS RoboMaker was designed to help developers solve these challenges. Let's deep dive. All right, but before we do, here's one of those AWS service primers. Here are a couple of the key services to know. First, Amazon Virtual Private Cloud VPC enables customers to define their own virtual networks in the cloud. You can easily define subnets and firewall rules through security groups that enable customers to securely run their resources in the cloud. You can run RoboMaker simulations in virtual networks you created using VPC. Amazon Simple Storage Service, or S3, is an object storage service in AWS with industry-leading scalability, data availability, security, and performance. You can use S3 to store things like robot application logs, software bundles, and more. AWS Identity and Access Management enables you to control and secure access to your resources that you've provisioned in AWS through defining permissions to users, groups, and roles. We'll highlight how IAM roles are used with AWS RoboMaker to allow your simulation to access services like Amazon CloudWatch, which is a central location in AWS to store your logs and metrics that you're capturing from your applications. These applications can be running both in the cloud, as well as applications collecting logs from physical robots in the field. At its core, AWS RoboMaker enables customers to launch simulations with a simple API call. The services provide built-in support for ROS 1 with releases kinetic and melodic, as well as ROS 2 dashing and beta. The service also supports Gazebo 7 and Gazebo 9. With a single click, you can open GUI interfaces for the Gazebo client, as well as common ROS development tools like RViz, RQT, and access to a terminal to interact with the running applications. All the logs, including ROS bags, are automatically recorded and written to S3 for further processing and replay. In addition to a physics-based Gazebo simulation, you can also run simulations with previously recorded ROS bags. And finally, if you're in the earlier session today, you'll have learned that we just announced a new feature that enables customers to dynamically generate 3D worlds. Today, this service supports generating randomized floor layouts and furniture configurations for home environments. There are multiple benefits to running simulations in the cloud with AWS RoboMaker. First is access to cloud scale. The service provides up to 15 virtual CPUs for each simulation, and you only pay for the amount of compute that you're consuming. In addition, you can horizontally scale by running hundreds of simulations with a simple API call. RoboMaker provides enterprise-grade availability with built-in health checks to ensure simulations run smoothly and reliably. The service is fully managed, meaning that you don't worry about provisioning and running the Gazebo software stack, and only need to focus on preparing your ROS application. RoboMaker is integrated with multiple AWS services, enabling you to easily extend cloud functionality like CloudWatch logs, ML services, data storage and analytics, and more to your simulations. Finally, with pay-as-you-go pricing, you only pay by the minute for the resources you consume. One simulation unit or one virtual CPU and 2 gigabytes of memory costs about 0.67 cents per minute. In addition to the simulation service, the RoboMaker team has created and published multiple useful assets to our open source GitHub repository. This includes cloud extensions that can be included in your apps to easily upload ROS bags to S3, connect to managed AWS machine learning services for things like text-to-speech, natural language comprehension, and image recognition. You can upload logs and metrics to CloudWatch, and finally you can use Kinesis to stream video from your robots into the cloud. We have provided multiple 3D worlds for Gazebo that can be used out of the box to accelerate your simulation development as well. Here's a link to our open source code assets. All right, so now let's see how this works. Before we launch a simulation job, there are a few concepts to discuss about how RoboMaker will run your simulations. RoboMaker enables you to define separate robot and simulation ROS applications, so you can decouple software packages and assets that are not required on the physical robot. While only one defined application is required, it is generally a best practice to separate the Gazebo worlds, including 3D models, actors, and plugins, including the robot descriptions and any simulation test cases and logic from your robot application. The robot application would include things like navigation software, any packages for perception, or robot sensor data processing. One thing to note is since the physical sensors, actuators, and controllers are simulated using Gazebo, you likely don't need to include any of the hardware-specific drivers that you need on your robot. In order to run a ROS application in RoboMaker simulation job, you'll need to build and bundle the application with Colcon. Colcon is a command line tool that improves workflows for building and bundling software packages and supports both ROS 1 and ROS 2 applications. It is compatible with Catkin, which is popular with ROS 1 developers, making it easy to migrate. The two main commands to prepare your application in a ROS workspace for RoboMaker is Colcon build and Colcon bundle. In today's first demo, we'll use a cloud-based development environment. In this environment, you can see that I've already cloned a sample ROS application. This sample application will spawn a PR2 robot in a hospital environment and is available in AWS samples at the link below. You'll notice both a robot workspace and a simulation workspace. The robot workspace contains the navigation and teleop packages for the PR2 robot. The simulation application contains the launch files and packages to spawn a virtual PR2 robot, along with the 3D Gazebo model assets for the hospital world. The first thing we'll do is set up our ROS workspace and run Colcon build and bundle commands for each workspace. After this is complete, we can upload our new bundles to S3. We will reference these when we start our simulation. Okay, let's create a new simulation job. The first section is the simulation job details. Here, we can set the maximum job duration, which we'll leave at the default of 8 hours. The failure behavior, if we should continue to run the simulation job in the event of an application failure, our ROS distribution, which today we're going to use melodic, and an IAM role to apply and grant AWS permissions to the underlying simulation job. Today, I've pre-created a role that gives the simulation job access to S3 to pull the bundles and write ROS bags, as well as to CloudWatch logs. To help manage costs, you can set a ceiling for the amount of compute or simulation units that are consumed by your RoboMaker simulation job. I'll leave this at 15 simulation units. We can then select the S3 bucket where we're going to store those ROS bags and ROS logs, and then select the VPCs, subnets, and security group we'd like to use for the simulation. For this application, we don't need a public IP. And then finally, you have the ability to set some tags. In the next tab, we'll create our new robot application. First, we'll need a robot application name, and then we'll need to select the path to the bundle we created in the previous step. The launch package name we'll use today is PR2 Hospital Robot, and the launch file is PR2 2D Nav. Then we can add environment variables. In today's example, we're going to use the environment variable robot, and we'll name it sim. In the final section is the RoboMaker application connectivity. This section enables you to map ports exposed from your application to the underlying simulation job. For example, if we need to open up a ROS bridge to another simulation job or an application running outside, we could open the port 9090. Today, we don't need any additional ports, so we'll leave this blank. Next, we'll go through the same exercise for the simulation application, except in this case defining the gazebo configuration. In this section, we'll add another environment variable for a starting pose of the robot. Okay, now let's launch. In a few minutes, we can connect to the running gazebo simulation application. You'll notice a gazebo GUI client, RViz, RQT, and a terminal are available. Let's open gazebo in RViz. We can add 2 topics in RViz to visualize some sensors, and we'll add a map. Then we can send a simple navigation goal to start building our map with the included SLAM packages. Okay, now we can watch the PR2 robot navigate within the hospital environment. Keep in mind the hospital environment is also open source and available in the AWS Robotics GitHub repository if you'd like to include it within your applications. And that's all we have for this demo. All right, so while the console presents a nice user experience to launch simulation jobs, in many cases developers want to programmatically run simulations using the API instead. AWS provides both a command line tool as well as a variety of different SDKs in Python, C, C++, Java that enable this workflow. You'll notice the same parameters that we defined in the console are available to be set in the command line. You can find more information on how to structure the parameters for various SDKs in our documentation. So in addition to running a single simulation job, AWS RoboMaker has a batch API to enable customers to run many simulation jobs. One key thing to note is with the start simulation job batch CLI command is the create simulation job requests. This is the array of the single job request parameters that we defined in the previous slide. For folks new to AWS, you can also store the parameters in a JSON file and reference the file in the CLI command. Since batch requests have a large number of parameters defined, this can be a nice feature in order to encapsulate the requests that you want to push. Okay, so now that we've launched some simulation jobs, let's walk through some common patterns for running simulations in the cloud with RoboMaker. But before we do, I have another AWS Primer slide for you. So here's a couple services that are helpful in building automated workflows with AWS. First is AWS Lambda, or Function as a Service. AWS Lambda enables you to run code in response to events without having to provision any computing resources. Step functions enables you to define and run workflows in the cloud to orchestrate activities like running your Lambda functions. We will discuss how to use these to orchestrate testing workflows. Next, we have Code Pipeline and Code Build. These two managed services enable you to quickly build continuous integration and delivery pipelines. Code Pipeline orchestrates the delivery workflow, and Code Build provides a fully managed build server to use when preparing your ROS applications. All right, so the first pattern we'll dig into is automated regression testing using simulations. An important part of the software release cycle is ensuring code changes don't have unexpected consequences on robot behaviors. So RoboMaker enables you to flexibly run these regression tests in simulation using custom parameters through the API. This makes it easy to connect existing CI/CD tools, which could be tools like Jenkins or Travis, with RoboMaker to run those tests. There are a wide range of test scenarios that are well suited for simulation. Low fidelity simulation can be leveraged when testing the communication pipeline, external fleet management software, or running software load tests. When scenarios require a physics engine to test real-world conditions, 3D simulators like Gazebo are a good option. Today, running Gazebo-based simulations in RoboMaker is particularly well suited for medium fidelity simulations to test things like localization, planning, and behavior algorithms. Finally, high fidelity simulations are required when your test scenarios include things like vibration behavior, slippage, and motor saturation. Robot application development and testing will likely include multiple types of simulations and simulation tools for different types of scenarios. So one extensible and repeatable way to define scenario-based test is through creating a set of environment variables. You can find a helpful simulation launcher tool in our GitHub repository that implements this pattern. Here you can see two scenarios are defined. In the first test scenario, we're testing to see if a robot can reach a single random navigation goal in a small house world. In the second scenario, you'll notice the navigation success count and the simulation world environment variables. We are defining a test to successfully reach 4 navigation goals in another world in the bookstore world. Finally, in the simulation runner below, you'll see the two scenarios that are going to run those create simulation job requests with these parameters defined as we discussed in the earlier slide. If you want to use this structure, take a look at the open source code in GitHub. AWS RoboMaker provides access to 2 services from your ROS applications to cancel and tag simulation jobs. In our regression testing workflow, we need to report the test results. Did it pass or fail? We can do this by self-tagging the simulation job. This enables downstream processing applications to get access to the test results with a simple describe simulation job API call. Secondly, once a test is complete, we want to stop the simulation job before the defined timeout to optimize our costs. We can do this by canceling the job. Here are a few code snippets that enable you to implement this logic in your ROS-based tests. Also is a link to one of our sample applications that includes a sample test node. Okay, so once we have our tests written and running in ROS, here's a sample architecture for implementing a testing workflow using AWS step functions in a CI/CD pipeline with code pipeline. Using a Lambda function, we can trigger a step function's job. The first Lambda function in the step functions workflow will run the batch API call in RoboMaker to start a batch of simulation jobs. Once running, a Lambda function in a loop will get the status of the batch job, waiting for each simulation job to complete. When any individual test within the simulation job is complete, the test results are tagged to the simulation job and the job is canceled. When all jobs are complete, if one or more tests fail, we need to send an API response to code pipeline from the Lambda function to end the CI pipeline with a failure. Also, if any jobs fail to run for any other reason, we can specify an error logic within the step function state machine to catch the error and fail the pipeline. On the other hand, if there are no errors and all tests pass, we can send the API call to code pipeline and succeed the code integration and prepare our application for the next phase in the release cycle. So bringing it all together, here's what a complete CI/CD pipeline could look like using AWS RoboMaker simulation as part of the workflow. So working on a developer feature branch, developers build and iterate using local development tools. Once ready, developers can issue a pull request and after a code review, merge their changes into an integration branch. This will trigger a code pipeline delivery job. The first step is to run Qualcomm build and bundle commands to create our new ROS application software bundle. After that is complete, code build will upload the build artifacts, that tarball, to S3. With the latest bundle in S3, the final step in the code pipeline is to trigger the step functions workflow from the previous slide. If all tests pass, we can safely integrate our code with the latest release branch and run the application in physical testing arenas before producing a release candidate to deploy our code ultimately to our production robots. Okay, let's see how this works in AWS. So we'll go back into the development environment that we were using for the previous demo to run this one as well. The robot application we're using today is our robot monitoring sample application, which you can find in the AWS Robotics GitHub organization. So let's say our customers expect our robot to be able to autonomously navigate in multiple different room layouts and locations. You'll notice in the JSON document, we have defined a set of environment variables for each scenario, testing for the behavior that our customers are expecting. Once these scenarios are defined, we can go ahead and merge our code changes into an integration branch. A webhook has been configured in GitHub with AWS Code Pipeline, a managed continuous delivery service, to start a new job. The ROS application will be built and bundled using Colcon in AWS Code Build, a managed build service. Once complete, a batch of RoboMaker simulation jobs are triggered and monitored through a set of compute functions running in AWS Lambda. Each simulation job runs a single scenario and, when complete, automatically self-terminates with the test results tagged to the simulation job. Let's open one of the simulation jobs. You can see that the robot is navigating to multiple goals. Once complete, the job will tag the test results and self-terminate. Finally, the results of all the tests are analyzed and the code integration is either passed or failed. Using RoboMaker for regression testing, iRobot has improved test coverage and can now run more than 40 automated tests for each code commit and 500 automated tests for every release candidate. This reduces the number of software defects and increases our code release velocity. The final pattern that we'll talk about today is fleet simulations with multiple robots, using horizontally scalable simulation jobs in AWS RoboMaker. Leveraging the built-in integrations with AWS VPC, RoboMaker enables you to easily connect concurrently running simulation jobs with each other. In this architecture pattern, we connect multiple simulation jobs, each running their own robot, to a single consolidated fleet simulation. Now, having access to connect simulation jobs to external applications running within the VPC, that makes it easy to run controller software or other applications within EC2 or other AWS services and have them communicate with your fleet. In this example architecture, the consolidated fleet simulation is running a ROS server. So we'll start off with a batch simulation API call that will start our simulation jobs. Each one of our robots is going to have their own namespace so they can identify one another within the fleet simulation. Finally, we're going to use this centralized ROS server to consolidate that robot data and provide our fleet level simulation. Any external controller software that's running in EC2 or on a container within Fargate or ECS, which are container services, can then easily connect to your simulation jobs. To try it out yourself, check out the GitHub link to the sample application. Now let's see a quick demo. In this final demo, we'll show a fleet simulation using AWS RoboMaker. Here is the implementation of the architecture you saw in the previous slide, with the single fleet server as well as the multiple single robots running in their own simulation jobs. On the right, we have a single robot running in a RoboMaker simulation. On the left, you can see that consolidated simulation with the two robots together. When we send a navigation goal in the connected simulation job on the right, you will see the robot moving in the consolidated simulation job on the left. Now, to enable robots running in separate simulation jobs to see one another, we're using Gazebo plugins to manage the interactions. Notice the outline of the second robot is captured with the LiDAR sensor data. This solution enables developers to work on complex planning algorithms and robot behaviors. It also enables you to horizontally scale to a large number of robots in a single fleet simulation. Bastian Solutions uses AWS RoboMaker today to run fleets of 35 or more robots to test navigation, orchestration, and inter-robot interactions. And that's a wrap. But before I go, here's a complete snapshot of the download links that I highlighted throughout the session. Okay, so I hope you enjoyed the presentation. Now's a great time for some questions.